Now we're going to discuss the definition of another quantity which is important in fluid mechanics, the circulation. So again, we consider a velocity field u, and here I'm going to schematically represent again this vorticity field with particle path lines or streamlines or whatever you want to call these. It doesn't really matter for this purpose. So let's consider a velocity field u, and now we're going to define completely randomly, like we define control volumes, we are going to define a contour. A contour is simply a closed curve in the 3D space. So this is my contour C. And we define this contour C as a closed curve in the flow field. So with this, we can define what we call the circulation, which most of the time we represent with the capital letter gamma as the line integral of the vector of the velocity field along this closed contour. So we're going to integrate along a closed contour. C is a closed contour, so I'm putting a round here of u dot dl, where dl is an differential element of displacement along the contour, and gamma here represents the circulation. So the way this would look like on this schematic here is, if you're thinking about this contour, right, at a given point along this contour you have a tangent vector t, and you can take a little piece dl along this direction, and so this vector dl is equal to a small displacement dl along the vector t. So this is our differential element of displacement along t. And so when you compute the circulation, what you do is that at this point you will have a velocity vector, right? So at this point, again, this is completely arbitrary. This contour doesn't exist. It's just something you imagine in your mind. If my velocity vector is u, you project u onto t and you multiply by dl. So you take u, the dot product between u and this dl, right, and you integrate as you move along this contour, and that gives you the circulation. So that's the mathematical definition of the circulation. So this is a quantity which you may not have seen before. So before we go further, let me show you an example of how you can compute this circulation on a simple flow that we've seen before, which is the Couette flow. So here is our Couette flow, and we can compute the circulation along any contour that we want. So I could take this here as my contour. I could take this here as my contour. So the circulation is really only defined on a particular contour. And sometimes this contour is given, sometimes you have to do it, but of course, you know, a contour like that would be difficult to control to compute the circulation on. So let me consider a simple contour, which is going to be this rectangle here. Okay, so we're going to take this contour as this rectangle, and we're going to move along these directions here. For the circulation, we're going to assume that this is at x and this here at x plus delta x, and the same in the y direction. We're going to assume that this is y and this is here y plus delta y, and we're going to integrate and compute the circulation on this contour. So here is our circulation, and so if our contour is this rectangle, you see here directly that this rectangle has four bits. We have this bit, this one, and that one, and we need to integrate along those four pieces of our contour. So we can split this integral in four pieces. Now remember that our velocity field for a Couette flow u is equal to, we have no component along the y direction, and our component along the x direction is linear in y, so it's linearly increasing in y, and is equal to gamma y. So I'm going to compute the first 2 bits here, and then the 2 others you can do on your own. So here, let's look at this first integral. So we can write this. We are integrating here along this direction. So what is our tangent vector? Our tangent vector is, so dl is equal to a differential element times the tangent vector. The tangent vector here is the unit vector in the x direction, and dl is just dx. Right, so we have to integrate. Our dl vector is equal to dx 0. Our velocity field is gamma y 0, and we're integrating between x and x plus delta x. Okay, this piece here, what do we have? Our dl along this bit of my contour, the tangent vector is the unit vector in the y direction. So our tangent vector is y, and dl is dy. Right, so when we write this piece, we have to write integral. dl is in the y direction, so it's 0 dy dot. Our velocity vector is gamma y in the x direction and 0. And we're integrating from y to y plus delta y. Okay, now let's compute these terms. This terms here, this term, it will be integral from x to x plus delta x of gamma y dx plus the integral from y to y plus delta x of the dot product between this vector and this vector, where this is equal to 0, because we have gamma y times 0 plus 0 times dy, so this is equal to 0, right? Plus the 2 others, which I'll let you do on your own. Clearly this one is equal to 0, right? And this one here is equal to gamma y times delta x, right? And you can see clearly here, when you're thinking about the circulation, when you're moving along one, look at the velocity field. The velocity field is in the x direction. When you project it along this direction, you're going to have a net positive component, right? When you integrate along this, you see that your velocity vector is normal to the direction of your contour, so this part is not going to contribute because you have u dot l, and that's going to be equal to 0. When you integrate along this here, along this direction, you see that your dl dot u is going to be negative, so there will be a net negative contribution. And when you integrate along this direction here, you see that you will have 0. Eventually, if you compute all of these, you find that the circulation gamma is equal to minus gamma times delta x delta y.